So I'm Isabelle Delaporte. I'm a research fellow at the University of St. Andrews. I'm working on the Migrant Life project. And so one of the things that we have explored as part of the Migrant Life project is to use machine learning techniques to study the lives of immigrants. So I'm going to discuss some of the advantages of using machine learning techniques in demography. I'm going to focus more specifically on random survival forest, which is a technique that can be used in life course and longitudinal research when you have time to event data. So there are many different machine learning techniques, so I'll focus on this particular technique. So let me start with the motivation. So the most common techniques that have been used to study particular events or transitions in the life course of individuals are the techniques of survival analysis. However, we know that these techniques have a number of limitations. So for instance, survival analysis methods cannot be applied directly in high-dimensional settings. So this is when we have many variables that are potentially important when we study one particular event. So there are issues of multicollinearity. It's also the fact that when you have many covariates, the coefficients start to be quite unstable and we can't really rely on the results that we have. It also makes it difficult to describe how individuals differ in their survival functions. And so because of this, it also makes it difficult sometimes to detect and visualize interactions. So recently, several studies have shown that non-parametric methods, such as survival trees or tree ensembles, can be a useful alternative to classical survival data analysis. However, in demography, we know that there are still very few studies that have used machine learning techniques and random survival forest more specifically. So this method has been mostly applied in biomedical settings. So here are the studies that you can find that are studying, that are more in the demography field. So one study is by DeRose and Padara. They show the usefulness of using a single tree methodology to examine the predictors of marriage formation among women in Italy. You also have a study by Bilari and al. That apply decision tree learning and classification rules to detect determinants of the transition to adulthood in Austria and Italy. So they make very nice comparisons between the transition to adulthood in the two countries by using decision tree learning and classification rules. And you have very recently a paper by Arpino and co-authors that have decided to depart from the strategy of using single trees, and they apply random survival forest to analyze the determinants of divorce among married and cohabiting women in Germany. We also propose our own application of random survival forest to analyze immigrants' fertility behavior in France with Hill. And so these two studies, I mean, in terms of how to compare random survival forest with a single tree methodology, a random survival forest relies on many trees. And this has been said that it has been argued that it might be more robust to rely on many trees rather than to have your results depending on one single tree. This avoids some issues of overfitting. We're going to see this a little bit more later on. So before we start, it's important to understand properly the method. So there are many different machine learning techniques. I'm focusing on the ensemble learning methods, which are part of the supervised machine learning techniques. So you have methods for classification and regression. And so among the ensemble learning methods, we have random forest. So this is in the regression category. And this random forest can be extended to right-censored survival or time to event data with random survival forests. So here you have, so this figure shows you how the method or the algorithm works. So the random survival forest method, as other ensemble learning methods in general, they aim to obtain what we call trees. by recursively partitioning a dataset into subsets that are called nodes. So you start with the main dataset in terms at the data preparation stage, and you're gonna take bootstrap samples, and you're gonna obtain trees, and these trees aim to classify individuals into classes based on the values taken by their covariates. So there are several steps involved when you run the algorithm. So the first step, you start with a fixed number of bootstrap samples that are drawn randomly from the main data set. This number of bootstrap samples leads to an equal number of trees. So here we have specified in the parameters we wanted to have, for instance, 1,000 trees. You can mention, you can specify a different number of trees. But this is the default number. There are also several options that are available for the bootstrap. So by default, about 63% of the original observations will occur one or more times in the bootstrap sample. 37% of the original data will not occur in the bootstrap samples. And these observations are said to be out of bag with respect to the bootstrap sample. There is also, when you use machine learning techniques, some vocabulary that you need to get used to. But so we have a bootstrap sample here that we use. The second step of the algorithm involves the splitting of the nodes. So this is when you grow the forest. So for each bootstrap sample, a survival tree is built. As you can see, for instance, on the figure, you have a tree that is built by randomly selecting features. So the features are the variables, the covariates that you have specified in your model, and you can specify the number of candidate variables with the parameter mtree. The third step of the algorithm consists in growing the tree to the full size under the constraint that each leaf node, so each branch of the tree, contains no less than a single unique event. You can impose additional constraints by specifying differently the parameters. You can increase the minimal size of the terminal nodes. This is the node size parameter. You can also limit the total number of splits. So this is the node depth parameter. So this is a bit specific, but I think as an introduction to understand the method, it's useful at least to kind of understand how the algorithm works. And so the last step, which is the most important for us, is step 4. So it's the fact that you're going to calculate your outcome, which is the cumulative hazard function of each tree. You're going to take the average of these predictions in order to obtain an ensemble cumulative hazard function of the out-of-bag data. So this is the predicted probability that we're interested in, basically. So this method has a number of advantages. I'm listing some of the advantages that we have by exploring using this method that we have identified. We're still at a preliminary stage, I would say, using this method. So if some of you have any experience using this method, that would be really interesting to know more in the discussion part. But so some of the advantages that we can already notice is that random survival forest first is quite useful to identify the most important predictors of a specific behavior. So this is when you have many variables. As mentioned before, there is no issue of multicollinearity. You can include as many variables in the model as you want. And it will always tell you whether the variable is important or not. So this is quite interesting if we don't have any hypothesis about the event or the transition that we're looking at. The second advantage, which is often argued when using machine learning techniques, is that it allows to reach a better predictive performance than conventional methods. And the last one is that you're able to include many variables. And so this is quite useful to detect and visualize interactions. So if you want to see the relationship between different variables at the same time, it might be easier using this method than when you use conventional methods. So I'm going to rely on the two recent papers that have used the random survival forest in order to show you, to illustrate these advantages, what we mean by that. So first, how to identify the most important predictors. So these are the results that were reported in the paper of Arpino et al. So they're trying to estimate or to predict the event of separation among married and cohabiting women in Germany. And so here they have included many variables, as you can see, on both partners. And there are several ways of knowing which variables are important when you use random survival forests. There are two ways, using variable importance and minimal depth methods. So here they have used VIMP is the variable importance value, basically. And the larger the value, the more important is the variable. So here they have found that the most important predictors to determine the separation status include the marriage status and overall life satisfaction of both partners. In our paper with Hill, we look at immigrants' fertility behavior in France. We compare immigrants with descendants and natives, and we examine the event of having a first birth. And we can see we have included less variables, but this is just our decision, because we wanted to focus on variables that we were interested in, but you can include as many variables as you want. And so here we have included these variables, and we find that the educational level is the most important variable to predict the event of having a first birth, for instance. The second advantage that I'm going to try to illustrate is the fact that it's quite easy to detect and visualize interactions. And this can be very useful if you want to do some exploratory analysis. If you have no hypothesis about what you're looking for and you want to know more what is behind your data. So for instance, here we have looked at the predicted probability of having a first birth. And we wanted to look at it, how the fertility behavior differ among migrant populations. So here you have I for immigrants, descendants, D, and N is for natives. So we have compared the predicted probabilities of having a first birth for 3 different groups. And we were thinking that it might be interesting to look at it at 2 different points over the life course of individuals. So by age 30 and by age 45, the predicted probabilities will probably differ. And we wanted to also look at the relationship between the predicted probability of having a first birth by educational level as well. So low, middle, and high is the educational level of individuals, and their birth cohort that is defined, that is precise on the right. So here, if we focus on the probabilities of having a first birth by the age of 30, we can see that the predicted probabilities do not differ considerably between immigrants and natives among low-educated individuals. However, if we focus on highly educated individuals, so still at natives have a much higher probability of having a first birth than immigrants and natives. So this is quite interesting, because sometimes we often focus on the average, or we look at differences across a number of groups, but it might be difficult to look at how the predicted probability differ among so many different groups by educational level and by birth cohort. So this really shows you how random survival forest can be used in order to know a bit more how the behavior differs. Then we look at, for instance, for the second birth, how these predicted probabilities differ. And again, we see that among low-educated individuals, for instance, immigrants have a much higher probability of having a second birth. This is by, 5 years after the first birth, and then you have 10 years after the first birth. And we see that among highly educated individuals, immigrants and natives' fertility differentials are much more reduced. So to conclude, we're not really interested in the results per se in this presentation, but I just wanted to illustrate how random survival forest can be used to detect interactions and to also identify the most important predictors. This method requires no variable selection. So this is quite important. It's really, we have to change a bit the habits that we have. And it's not, we're not testing an hypothesis. We're really trying to know a little bit more what could be hidden in the data. And so this method can be used for this objectives. The last thing that I wanted to mention is that we know that machine learning techniques in general have some limitations. The most notable drawback of machine learning techniques in general is that the models are often black boxes, and it can be hard to interpret the results that you obtain. We don't have, for instance, confidence intervals. We don't have what we're so used to in order to be able to properly interpret the results. But we think that it can represent a suitable tool for exploratory analysis of survival data. And I look forward to hear your thoughts on that. Thank you very much.